Hello, so let's take a look at some cycloalkanes and think about their conformations and the potential strain energy in the molecule and examine whether that strain is from angle strain or torsional strain, as we talked about in the last video. So what is angle strain? So the German chemist Bayer came up with this idea that the sweet spot for a carbon, its optimum level of comfort, was in the tetrahedral stance, sp3 hybridized, with a bond angle each time of 109.4 degrees. That's as comfortable and as strain-free as the carbon can get, stretching those chemical bonds as far away from each other as possible. What Bayer speculated on was that if that angle decreased or increased significantly, it would start to create angle strain in the cycloalkane, something that we call Bayer angle strain. So let's investigate that. Cyclopropane has a drastically reduced bond angle in cyclopropane, just 60 degrees each time, much smaller than the 109.4. So Bayer predicted that it would be angle strain in cyclopropane. Even cyclobutane has a reduced angle down at 90 degrees, which should create angle strain. Likewise with cyclohexane, an increased angle of 120 degrees from the 109.4 that should create angle strain, but the cyclopentane should be pretty close to that sweet spot. That angle each time of 108 is very close to the optimum of 109.4. So Bayer predicted that cyclopentane would be strain-free. Let's see if he was right. So starting with the cyclopropane, one of the best ways to get an idea of how much strain there is to compare the combustion energies for open chain propane and compare that to the cyclic cyclopropane. So the heat of combustion for propane itself, C3H8, would be a total of 2220.7 kilojoules roughly. If we look at the energy for each of the three CH2 units, adjusted slightly, that comes to about 658 kilojoules. When we compare that to the cyclic cyclopropane rather than the straight chain, the heat of combustion for the cyclic compound is about 2091 kilojoules. And again, taking that every CH2 unit each time, that comes to about 697, which is a much higher energy per CH2 unit compared to the open chain at 658 kilojoules. That's 697 per CH2 unit is 39 kilojoules more energy. And so multiplied by the 3 for the cycle, that would be a total of 117 kilojoules. And that appears to be the total strain energy for cyclopropane compared to normal propane. So what is that strain from? Well, if we look at a Newman projection through any one of those carbon-to-carbon bonds, we actually find that the carbon to hydrogen bonds attached are eclipsed in cyclopropane. So that's going to create some torsional strain in the molecule, 4 kilojoules each time, another 4 kilojoules before, and we see that again from carbon 2 to carbon 3, above and below the plane, and also from carbon 3 back to carbon 1. So 6 times over, creating 24 kilojoules of strain energy, but that's specifically torsional strain between bonding electrons. However, we can still say that Bayer was mostly correct and say that 93 kilojoules of that 117 was probably because of Bayer's angle strain. Let's look at cyclobutane. Again, we'll compare the combustion values for normal butane, C4H10, and that has a total energy of 2879 kilojoules per mole. We break that down into the energy per CH2 unit, because 4 of them. Adjusted slightly, that comes to about 658. Compare that to the cyclobutane. That's a total energy of about 2744 kilojoules. Break it down by 4, roughly, with a couple of adjustments. For every CH2 unit, that would be 686 per CH2 unit. Compared to the normal butane at 658, every CH2 unit in the cyclobutane has 28 kilojoules more energy, which is no doubt strain energy. So multiplied by the 4, it gives a total strain energy of about 112 kilojoules per mole. But again, is this angle strain, or could it be partly torsional strain? So if we look at a Newman projection again, there is a slight buckling in the ring, so it's not entirely flat. And that's something that Bayer didn't take account of. Bayer believed that all the cycloalkanes were flat molecules, but cyclobutane is not. It's very close to being flat, so there's a slight skewing of the carbon to hydrogen bonds, but we can still pretty much, for the most part, treat them like they're actually eclipsed behind each other, although this is a very slight exaggeration. But if we make that assumption, again it's 4 kilojoules of strain energy between the hydrogens each time. So 4 above, 4 below, and the same 4 and 4 for carbons 2 to 3, 3 to 4, and 4 back to 1. So that creates a total of 32 kilojoules of strain energy, which is specifically torsional strain, bonding electrons getting too close to other bonding orbital electrons. But the vast majority, 80 kilojoules per mole roughly, is still something that we have to put down to Bayer's angle strain. So he appears to be correct for the most part here as well. If we move to cyclopentane, remember that's one that Bayer predicted to be strain-free, and we look at those combustion energies. First off, again, the normal pentane, C5H12. Total combustion energy, just over 3,500. The energy per CH2 unit is roughly about 659, and that closely matches the energy we see for the CH2 units in the cyclopentane ring at 664, just a little bit more than what we see per CH2 unit in the normal alkane. So 5 kilojoules of strain energy each time, and we see that 5 times over for the 1, 2, 3, 4, 5 carbons, of course. So it looks to be that there's about 25 kilojoules of strain energy in cyclopentane compared to the open chain pentane. Again, is this angle strain or is it torsional strain? So if we take a look and imagine what that strain energy total would be, with it being 4 kilojoules between each pair of hydrogen bonds, and then multiply that by 10, 1, 2, and then a second, third, fourth, and fifth time around the ring, that would be 40 kilojoules of strain energy. But our total is apparently only 25. So what's going on here? Again, it's about Bayer incorrectly assuming that cycloalkanes were flat, when cyclopentane is actually puckered. So we can show that with our diagram up here. Just try and move one of the carbons to that elevated position. It's a little bit like the flap of an envelope. As you fold it around towards sealing the envelope, we've got this puckered part at one end of the molecule. The carbon ring has a bit more flexibility and a bit more wiggle room, would be the layman term. So what does that do to our conformation for cyclopentane? Well, around the back of the molecule, from carbon 2 to 3, 3 to 4, and 4 to 5, the carbons and the attached hydrogens are pretty much in a eclipse conformation, which is creating strain energy. And it's only at the apex here, from carbon 4 to carbon 5, and carbon 5 to carbon 1, there we go, and carbon 1 to carbon 2. As you look down the bond through a Newman projection for those two, it actually looks like a staggered conformation because of that puckering of the first carbon. So as we calculate the strain energy, we're only seeing strain energy around the back, torsional strain, which comes very close to that total strain energy of the molecule, 24 compared to the estimated 25 through combustion. So Bayer was sort of correct in that he didn't think there was angle strain in cyclopentane, but he was incorrect to think that there was no strain. There is, because of the eclipse conformation around the back, some torsional strain, which pretty much makes up all the strain energy of cyclopentane. Looking at cyclohexane, something that Bayer predicted to have angle strain again, because of that bond angle each time of 120 degrees. We look at the combustion values for it. It's about 4198 kilojoules for the entire normal hexane molecule, giving us an average about 658 kilojoules per CH2 unit again. And if we compare that with the closed ring of cyclohexane, we get for the strain energy 3951, which per CH2 unit is about 658. As we just adjust slightly for the ring, it's pretty much a match, so it looks like there's zero strain energy in the molecule. That is not what Bayer predicted. So what's happening this time? Again, it's tied into the fact that Bayer assumed that cyclohexane, like the other cycloalkanes, was flat. But cyclohexane is not. Again, there's wiggle room. And so as we look at the bonds, they are puckered, but not just at one end like cyclopentane, they're actually puckered at either end. So one end dips up and the other end dips down. If we try and draw this for a cyclohexane ring, it looks kind of like this. So if we draw two parallel lines next to each other, sloping down, and just have them slightly askew from each other, that gives us the first four carbons in the ring. And then for the apex carbon, excuse me, the apex on one side, as the bonds are sloping down, your last carbon puckers back up. So put one in there and connect it to that one there. We've got one end of the ring. And on the other side, as the bonds are sloping up, that last carbon is puckering down. So about there, and back to there, and we have a six-membered carbon ring. So this is the best way to show the ring, this kind of staggered puckered stance. And so from one carbon to the next, the CH groups attached are actually staggered to each other. So this explains why there's zero strain energy. Remember from the last video, carbon to hydrogen bonds, which are staggered, do not invoke strain energy. And it's the ability of the molecule to undulate back and forth because it isn't flat, which makes sure that the molecule cyclohexane has zero strain energy. Just while we're here, if you want to draw the hydrogens attached to each carbon, remember each carbon has two hydrogen bonds. For each bond, if the apex is pointing up, then we have our carbon to hydrogen bond, which is pointing up. This is what we call an axial carbon to hydrogen bond. I can just write that in. So bonds that point straight up or straight down are axial bonds on the cyclohexane ring. For the second of the two bonds on each carbon, with an axial, there's also an equatorial. And if the axial is pointing up, the equatorial is sloping just slightly down to give us that 109.4 degrees bond angle each time. And so these bonds, which are roughly parallel to the plane of the ring, these are what we call equatorial bonds. And every single carbon has a combination of these axial and equatorial bonds. So we can go around the ring. For the next carbon, the apex is pointing down, so the axial hydrogen bond is going to be pointing down, and the equatorial pointing on the other side of the plane, just slightly up. Here, the axial is pointing up, like that. The equatorial is just slightly bending down. The axial pointing down, the equatorial ever so slightly up, the axial up because the apex is pointing up, and the equatorial slightly down and below. And the last one, axial pointing down, and the equatorial just pointing to the sides. So every carbon in a cyclohexane ring has two carbon to hydrogen bonds. One of them is axial and one of them is equatorial. And just as the axials alternate between being above and being below the ring, the equatorials alternate from being slightly below the ring to slightly above the ring to slightly below the ring again. In the next video, we'll look at strain energies in cyclohexane derivatives and look at both torsional and sterical strains as we look at the 1,3 diaxial interactions.